Hey everybody. What you're going to end up seeing here is a clip from a bigger video on solving systems by substitution. What you're going to see is a walkthrough on some formatting and the algebra, the thought behind using substitution to solve a linear system. And then you'll have a second problem to just be able to give it a shot and see how well you do with it. Okay, I hope this clip helps. Good luck. So, what you see on the screen right now is a system of equations. And all we're talking about when we say system of equations is we're talking about multiple equations. So that's all. So when we talk about a system, we're just talking about having multiple equations. So rather than just one equation being true, we have several equations being true. What you see in the system given here, two equations being true. So I'm assuming at this point we understand what solving a system means, that we are finding the point of intersection, or we are finding the x and the y values, in this case, that make both equations true. So theory-wise, I'm hoping that we understand that point. This is a process about how. So what I want to talk about is some formatting. So you're going to see me go through and put everything in blue that would be considered communication as part of your solution. These are necessary things that we want you to write down to make sure that your reader understands the process you're going through. These are also things that when you can build this into a habit, it starts to drive your thinking. So you'll find, if you choose, and you should, to include the blue in your solutions, they almost become a reflex for you that's going to start to drive how you go through and solve systems. They're actually going to make it easier for you to solve. Okay, let's take a look at A. We've been given the instruction to solve, so we need to find, in this case, the x and y values that make both equations true. So the first thing we want to do is be able to talk about these equations. So I'm going to call maybe the first one equation 1, doesn't have to be 1. And I'm going to call the second equation, equation 2. It doesn't have to be 2, but I don't know why you would start with something different. So by me writing down a number and circling it, I just gave that a universal name. Everybody now who sees those two equations can refer to those as equation 1 and equation 2. So that's what we're going to do. We're going to talk about them as equation 1 and equation 2. Now, for us to go through and solve using substitution, we have to go and get to a point where we can create an equation that we can solve. And what that generally is going to mean is we want an equation that has one variable in it. So you'll notice that both of these equations have two variables in them. So individually, we could not solve for the value that a variable is with any individual equation. But if we can combine these two equations in a way that would create an equation with one variable, then that would give us the means to solve. So what I'm looking to do is somehow take equation 1 and write it all with x's or all with y's. Or I'm going to try to do the same thing with equation 2, write it all with x's or all with y's, because I can solve any equation with one variable. So the way that I can do that is to substitute one of the equations into the other one by replacing the variable with an expression that it's equal to. Now, some of us, because we have some experience going through and dealing with equations of lines and thinking about it from a graphical standpoint or a properties of line standpoint, we can sometimes get the sense that what we have to do is isolate an equation for a y. And I need us to know we don't have to do that. That quite often we'll rearrange equations of lines to get the y all by itself, to be able to look at properties of a line, like the slope of the line or the y-intercept of the line. But for the purposes of solving a system, we don't need to get the y all by itself. So what I want to do is I want to take a different approach, intentionally take a different approach. I'm going to isolate and get the x all by itself, just because I assume everybody has a default to get the y. So I want us to take a look at both equations, equation 1 and equation 2, and imagine rearranging either one of those equations to get the x all by itself. What you'll notice if we think about that process is it's going to be easier to get the x all by itself in equation 1 rather than equation 2 because you will not have to divide out that 3. So for the purposes of strategy, if I were you, 100 times out of 100, I'm going to take equation 1 and I'm going to try to get the x all by itself. So I'm going to take equation 1 and I'm going to start to isolate x, which means I can copy out equation 1 and I could just write equation 1 down like that if I wish, and then spend a line going and getting rid of the y to be able to isolate x. But please don't ever feel like you have to waste that first line. If I were you, since equation 1 is relatively straightforward to isolate, I think I'm just going to get rid of the y. So when I write down equation 1, at the same time I'm doing that, I'm going to isolate my x. Now, take a look at what I've written on the screen. Everybody should understand that that equation is equation 1 because I've labeled it as equation 1. Nobody should be looking at that gold equation and going, gee, where did that come from? Because I use my blue equation label, everybody can see that that's equation 1. And if they reference back to the original equation 1, they can just see that it's a manipulation of it. Okay, now that I have that equation 1 isolated for one of the variables, for x, I'm going to sub that into my other equation. What I just came up with, and what I just underlined there in orange, is what x is equal to. It's equal to negative y minus 1. So, wherever I see an x in equation 2, I can replace it with negative y minus 1 because they are equal. So what I'm going to do is I'm going to sub equation 1 into equation 2. And you can see in my blue writing, I am telling the world that that's what I'm doing. Now, I could waste a line copying out equation 2 exactly as it is written to then replace the x with what it's equal to. But please feel free. You could go through and start copying out equation 2, and right as soon as I'm about to write that x, I'm not going to write that x anymore because I know that x has a value or is equal to negative y minus 1. I replace my x with what it's equal to, and I copy out the rest of equation 2. There is the act of me subbing one equation into the other. And if you've been watching this video since the very beginning, you'll notice that's what we did in problem 1, part C. We took a multi-term expression and we subbed it into another equation, and look at what the outcome was. We now have an equation with just one variable, in this case, y. And we should be pretty solid to be able to go through and solve equations in one variable. So I assume that we're pretty solid in where we go. We could go through and expand our brackets. We could then continue on, put together our variables into one variable term, get our constants together, And now we could go through and isolate our variable. There we go. So we solved part of our problem. That is, we ended up creating an equation with one variable, which allowed us to solve for y in this case, for one variable. Our problem was our original system had two variables. So we ended up finding the y value that makes both of those equations true, a y value of -3, but we don't know the x value that makes that true. So to go through then and find the x value, we're actually kind of taking a step back. I think this is probably pretty straightforward. All we need to do now is just sub that y value that we just found back into one of our original equations. So if we look back up to our original system, you see equation 1 and equation 2. Since that y value works for both equations, then we could sub that back into either one of our originals to find its coordinating, its matching x value. So when you take a look back at that system, I really hope that you're thinking about the ease of your work. And therefore, I would hope that we would sub it back into 1. Now, I'm not saying it should be difficult for us to sub y equals -3 back into equation 2, but it is going to be more work. We're going to have to calculate some stuff. There's some bigger numbers involved. And so by subbing it back into equation 1, we're making our life about as easy as it could be. Replace my y with a -3. And now we have an equation with one variable again, with x. Now we can go ahead and isolate that variable, and because we chose the easier of the two equations, then I should have the easier work to be able to go through and solve that equation. And so we've come up with an x value of 2. We have now solved the system. We know that an x value of 2 and a y value of -3 are what make both of those equations true. Now, I'm going to skip the process of us actually taking 2 for x and -3 for y and subbing it back into both equations to confirm our solution. I think that should be okay on your end. The only thing to do to finish off the problem is we actually state our solution as a point of intersection. Or we list the solutions. And we always make sure that when we list them in alphabetical order. So x comes before y. So when I list out my solutions, 2 comes before -3. And there we go. We solved the system using substitution. Now, take a look at the screen because you can see all of our algebra in yellow and you can see all of our communication in blue. I'm telling you that the more and more you practice writing out that blue, you're going to turn solving systems into a reflex action. So make sure that that blue is included in every one of your solutions. Okay, let's try another one. So what you see on the screen now is a system for problem B. I have 2 equations again, and I've been given the instruction to solve. So let's make this as automatic as we can. Label both of your equations, equation 1 and equation 2. Now I want to make a determination of which one of those equations would be easier to isolate for a variable. I scan across all of my equations. Notice I have a coefficient of 2, a coefficient of 3, a coefficient of 2. Those 3 values that I just circled, if I were to isolate for their variable, I would have to divide out that coefficient, which means I might be getting some fractions. However, I've got this y term in equation 1 that has a coefficient of 1. So I would, in essence, have nothing to divide out, which means I can avoid some fractions. So if I were you and I was scanning those equations, I am looking for a variable that has a coefficient of 1 if I'm going to use substitution. And so I see that in equation 1, so I am going to take equation 1 and I'm going to rearrange it. Now, I like to think about my variable term with a positive coefficient. So I'm actually going to think about my y being on that side of my equal sign. And so that y would just be a positive y on the right. That means I want to get rid of that 2, so I'm going to get it over to the other side, which means to get rid of a plus 2, I minus 2, and there is equation 1 isolated. Okay, now that I have equation 1 isolated for a variable, I'm going to take that one equation and sub it into the other. So I'm subbing 1 into 2, so I can now copy out equation 2, but wherever I see my variable of y, I can replace it. And since I'm subbing in multiple terms, I'm going to sub it in brackets. That way I maintain my multiply operation. Okay, now I have a nice easy equation. It's all in one variable. Now is a moment where I think we should be picking this stuff up on our own. So what I want you to do is I want you to pause the video and solve that gold equation that has just x's in it. Okay, give it a shot. Pause it now. Okay, we're back. So I can expand my brackets. Now I want to isolate. So I put my variables together, put my constants together. I'm running out of room. And so I'm going to draw my arrow, and now I can isolate by dividing out 7. Okay, we're good. We've now solved for one of the variables, but we need the other one. So I now need to take that x value, the one I just solved for, and I have to sub it back into one of my originals. Well, if I take a look at equation 2, it's got bigger numbers. Equation 1 has smaller numbers. I'm going to sub x equals 4 into equation 1. So that's going to give me a 2 times 4. And in a lot of cases, you're going to skip that step. You're going to come right in on 8 minus y equals 2. And now we can solve. And however you want to solve for that, I'm hoping that we get down to a y value of 6. Okay, we're almost done. We've actually done all the work. We've solved our system, but we haven't stated our solution. So state your solution as a point of intersection. The x value comes before the y value. And there we go. You'll notice this is the same approach that we took in our solution to A. And you'll also notice that all that blue is driving my thinking. Don't skip the blue. Okay, keep it within each solution. Okay, let's keep working our way through. Let's try another one.